Okay, welcome everybody once more to the official IAU G2 online conference series. As usual, this is about massive stars. And today is my great pleasure to introduce our next speaker, André Oliva. André is, since a few months ago, an invited professor at the Space Research Center and the School of Physics of the University of Costa Rica, while also keep his affiliation of ad honorem external collaborator at the Observatoire de Genève. After performing his bachelor and master studies in Costa Rica, he moved in 2018 to Germany to develop his PhD thesis under the supervision of Rolf Kuiper at the University of Tübingen. And it was in 2022 when he defended his thesis entitled Modeling Disks and Jets Around Forming Massive Stars and a Look at a Remnant Neutron Star. Maybe he will explain why this second part of the title of the thesis. After that, and before moving back to Costa Rica for his present position, he performed several postdoctoral stays at the University of Heidelberg, the Observatoire de Genève, and the University of Duisburg, Essen. His main research interests focus in the theoretical modeling of massive star formation. However, as you can see in his personal webpage, that is, I found it amazing. He's also very interested in many other things related to teaching, outreach, programming, graphic design, and music. And probably I forget some of the things. So thank you very much, André, for accepting the invitation of the IAU G2 Commission to deliver this online seminar, especially being so early for you in the morning. Whenever you want, the floor is yours.
Thank you very much. Actually, I'm very, very honored for the invitation, and I really want to express my gratitude to allow me to share a bit of my work. And yes, exactly as Sergio was explaining, I am starting a tenure track position at the University of Costa Rica, but maybe we can switch to the first slide where I can show you a bit the map to keep track. Yes, exactly. I did my master's, my bachelor's and master's thesis here at the University of Costa Rica. And actually my topic at the time was neutron stars. So this is why there's this the second part that Sergio mentioned in the title. It was a relatively small work on pulse profile modeling, so modeling of pulsars. And I have kept this a little bit on the background, but still working a little bit on this. Even here in Costa Rica, I will show this in the next slides. I think the second after this one. And then I did my PhD at the University of Tübingen, stayed for 8 months in Heidelberg. Then it was a bit in Duisburg, then in Geneva for a Swiss Government Excellence Scholarship. There was a postdoc for 1 year at the University of Geneva. And then the last 6 months before coming to Costa Rica, I spent in Duisburg with my former PhD supervisor, Rolf Kuiper, who has now a very amazing group in Duisburg that has started relatively recently as well. I would like to say very, very quickly, well, I really enjoyed my time in Switzerland, in Geneva, but I am very saddened to see the ongoing news of an avalanche, and my heart goes to the people of Platten in the Lürchental in the canton of Valais. I really enjoyed a lot the mountains, the Alps, so I hold this very, very dear. And even though it's a geological process and Swiss are used to this, but I hope that everything resolves very, very quickly. I would like to present to you, this is the research group that essentially we have come together and assemble in the past month since I arrived in Costa Rica in March. As you see, it's color-coded. I have some master students who are starting their thesis, others that are not entirely sure yet, but still are joining our group meetings. This was the group meeting last Tuesday. And I also have several bachelor students. Unfortunately, how it works for us, it's a bit hard to have PhD students, but Brian Hidalgo is going to start his PhD with me very soon. And actually, Brian and René, they are working on neutron stars, and the rest is working with me in massive star formation. So actually, for me, it's a very, very exciting a new step or epoch of my life. I also put again the map where Costa Rica is. The University of Costa Rica is one of the public universities in Costa Rica, is the largest public university. And we have the CINESPA, which is the Space Research Center belonging to the university. And I have, at least in an interim way, put this name for the group, the research group, BEWA, which means star in one of the indigenous languages of Costa Rica. And because we have several topics, this is what I have come up with. But this is at least interim, the name of our group. This talk is a bit ambitious. I will try to do my best. First, I will start with an overview of the problem of massive star formation, because even though this is a specialized series of talks on massive stars, nevertheless, it's not tailored to massive star formation. So I will bring out a little overview, and then I will give you a tour for some of my recent work, and even ongoing work at the end of the presentation. First, I would like to show you some pictures that are some illustrations that I did for a review that was published very, very recently by Henrik Beuter, Rolf Kuiper, and Mario Tafalla in annual reviews about our present understanding of massive star formation, how more or less we understand the process until now, or at least up to now. We think of cloud dynamics as a relatively turbulent process where there is formation of filaments, breaking down of those filaments to form stars, etc. And we understand there are some spots in the clouds, generally in clouds, where there are converging flows that are high, that bring high enough amount of material in a short amount of time to form high mass stars. And as you see, the scales there is more or less, we're talking about 5 parsecs. And I do always this in presentations, because it's very, very easy to get lost when one talks about star formation, about the scales and what are the differences, qualitative and quantitative, that we see in when we talk about star formation in those scales, in high mass stars, low mass stars. At least for low mass stars, this is more or less the process that we believe is happening. Filaments that are breaking down due to gravity. And essentially, this is how the classic textbook GENES process works. And in high mass stars, as I was saying, yeah, we believe that those are filaments or filament hubs that bring material to massive star formation regions. Although this is not fully understood, there are still several scenarios that could be possible. There is not even a consensus on whether the magnetic fields guide the flows in this case, or vice versa, whether the magnetic fields are perpendicular or parallel to the filaments in the clouds, etc. So those are the kind of problems that will keep us busy as a community for a long time. If one goes very close into one of those star-forming regions, one of those cloud cores or dense regions of the cloud cores, then eventually one would encounter an accretion disk and outflows that are launched. And this is more or less the important scale that I will discuss during the presentation. So I will more or less skip this, but I would like to mention then what makes massive stars, or at least massive star formation, different than low mass star formation, apart from the mass itself, is the fact that high mass stars bring a lot of stellar feedback. And stellar feedback is composed by all the radiation once a star is formed and starts to produce photons, in particular UV photons, can ionize the medium and bring important amounts of stellar feedback, so radiation forces etc., to the material. And this in turn can even, again, another topic that is high, well, where there is a strong amount, a big amount of research at the moment, is whether this can trigger future star formation processes within the same cloud. I would like to just show you, this is a simulation that was done in Heidelberg, not by me, but I was collaborating to try to get some information out of this simulation. It was done, or at least analyzed by my colleague Glenn Hunter in the group of Ralph Klessen at ITA. And this is one of these other scenarios. For example, here there are two molecular clouds that are colliding and creating those high flows of mass to form even massive stars. But most of the stars that are formed in this simulation are low mass stars. But just to illustrate the larger scale process, here you see the scale around 10 parsecs. And so again, when one talks about star formation, this is the thing that's there are so many scales involved, from inside of the star up to the galaxy, which would be for massive star, for star formation people, larger scales or large scales, but for people who do cosmology, this is very small scales. And still there is star formation still contributes to everywhere in those processes. And so because one can get lost very, very easily in these presentations, what I do normally is to put a scale in there as a reminder of what we are doing and where I am talking about, and a slider to show where we are. So first, I would like to talk about the first project that I did as a PhD student in Rolf's group in Tübingen at the time, which is about multiplicity explained via disk fragmentation. So what is the contribution of disk fragmentation towards the multiplicity of massive stars? And for this, what we do is we take one of these dense regions in clouds, as I have shown in these other simulations, and we model it in a very idealized way, at least at the beginning of the simulation, with a smooth density profile. In this case is a 200 solar mass cloud core. This is to create a certain accretion rate. Is not that we can enclose 200 solar masses without any kind of turbulence or any mechanism to keep it there in a region of 0.1 parsecs in radius. But the idea is to achieve the kind of accretion rates that are typical for massive star formation. So these initial conditions are very idealized, but they allow us to proceed. Actually, this is part of what I was doing by comparing the simulations that I mentioned with Glenn, and so we see that there are ways to justify this scenario. And this cloud is slowly rotating at the beginning. There is a profile for density and also a profile for the angular velocity as a function of spherical radius and cylindrical radius, respectively. And we also consider present-day massive star formation, so current metallicities in the solar neighborhood, just to also be clear for all the communities. And in this case, we are not going to take into account magnetic fields. And so if you let the simulation evolve for a while, then what happens is that this disk becomes massive, massive enough for gravity to start competing a little bit against the massive protostar that is going to form at the center of the cloud. And so then self-gravity acts and the disk starts to break down, first forms spiral arms, and then those spiral arms form fragments, as the process that I was showing that also happens at larger scales. Then you also see something similar at the smaller scales, with the exception that in this case we have rotating material, and also the shear can bring some stability. So you need to take that into account. It's not the Jeans criterion, but it's what we call the Tumre parameter, Tumre criterion. And so the physical ingredients for this simulation are the gas hydrodynamics that we model with the code Pluto by Andrea Mignone et al., and several modules that were implemented by Rolf Kuiper for self-gravity and all the thermodynamics. So stellar irradiation, so what the star is, in particular here, we only consider the heating that the star is going to give to the material of the disk, especially the inner disk, thermal re-emission from the dust and gas in the disk, dust sublimation and evaporation, and stellar evolution they are incorporated as evolutionary tracks from which we interpolate. And essentially the idea is to know what the protostar and then star is doing to compute what the correct heating to the inner parts of the disk should be. Well, and the modules are named Aumea and Makemake. I will mention still that this is a time-independent spherical grid, but because it's refined with distance, even though the refinement never changes as a function of time, we achieve very, very high resolutions, sub-AU resolutions, very close to the protostar, and we are able to see, you will see in a moment, several very interesting physical processes. And they are still, even though this is 5 years old, the highest 3D resolution simulations to date with this kind of physics, all completely included. And there are no sync particles needed in this kind of simulation, so which is very, very good, because this allowed us to study the first stages of the formation of companions in the accretion disk. So now you're about to see a movie of the mid-plane cut of the disk. So now the movie is not playing, but you see here already the formation of spiral arms and the accretion disk. And before I press play, just keep in mind that the numbers that you're about to see, they are just the tracking of those fragments that the disk forms. They are not sync particles. And so here now I am playing the movie, and you can see that fragments form, they interact gravitationally, migrate, merge, get sheared, they develop secondary disks around them, for example, that 21 that you see in there, or that 40. And then some of them get accreted by the central massive protostar. But it's not so easy, because the white dot that you see at the center of the simulation is our internal boundary in the simulation. We can't compute beyond that, because the simulation gets progressively, very strongly stopped by the decreasing time step. And so because of this, we have to develop some model to see whether the fragments would be accreted or not be accreted, our best guess at least, when they go inside of the sync cell. So that they go inside of the sync cell doesn't necessarily mean that they are not going to form a star, a companion star. The idea of the study was to see the companion formation, and in here what you're seeing is a vertical cuts of the same accretion disk and several processes. Here one sees very clearly the gravitational collapse radial towards the center of this fragment. This is fragment 12 in the picture, in the movie that we saw before. And one sees this whitish colors in there, which is density, is a region of very high density. And that's when I compared against some simulations that do take care of resolving what those stages of the formation of a protostar are by Asmita Bandari. Then we discovered agreement. We are actually resolving the first stages of companion formation by almost resolving, at least with a few grid cells, the hydrostatic core. So we see the first Larson core in this whitish pixels or cells that you see in that picture that is on the screen right now. And also you see that the fragment gets quite flattened, and this is because there is a disk that is forming around it. And this is one of the disks, the secondary disks that we saw before in the movie before. And what we can do is to track the properties of those fragments. And so in here, what I take as a key parameter to see whether those fragments can further evolve or not was to keep track of the central temperature of the fragment. And if the temperature of the fragment goes consistently beyond 2000 Kelvin, even though the following is not included in the simulation, it gives us an idea of what will happen. What would happen is that beyond 2000 Kelvin, the gravitational energy from the collapse is used not to increase the temperature inside of the fragment and therefore the thermal pressure, but rather is used to dissociate the hydrogen molecule, because most of this gas is H2, so diatomic hydrogen. But at some point, then when the gas becomes too hot, then this molecular hydrogen is dissociated. And because the energy is not being used to increase thermal pressure, then there is a collapse. And this is then the formation of the second Larson core that should be a few solar radii of size. And the argument is that once this step has taken place, then is most likely the case that the second Larson core is way more stable, at least against the gas pressure that surrounds the gas. So it has way better chances to become a companion star than a first Larson core it would be. And so in this case, you see this illustration. By the way, the circle on the center of the screen is the same size as the circle at the left side of the screen. So it gives you, so if you manage to see the white dot at the center of that central circle, the relative scale more or less of the second Larson core compared to the first Larson core. So this is why we believe it should be way more stable. And the idea was to produce some statistics with this, and then one can predict the wide orbit companions, so few thousand, 1000 AU more or less of the size of the orbit, and close companions around 4-ish. So those numbers mean that we expect a few companions of the order of a few to 10 or something this from the simulations. And the masses, those are the masses that we compute from the simulations, but that doesn't mean that those are the final masses of the companions that are produced by this fragmentation, because the process is not completely modeled in here. And the masses could grow. They have their own disks around them. So actually, this is not necessarily the final mass, but it gives you an idea of what can be done. Okay, so now I would like to talk about this, the main topic of the talk, which is protostellar jets and their magnetic origin. For this, I will show in the next few slides a presentation specifically about this topic that goes into a zoom in and an interplay between observations and simulations. So to keep track of everything, keep in mind the following legend: everything that you see, it's blue. With the blue label is the simulations, and everything with the orange labels is the observations, and some technical details. Some of them I will mention, some of them not, are in black boxes, I think, pretty appropriately done with the graphic design. So here, then we model again one of these cloud cores, very similar setup compared to the one that I have mentioned, with the density profile, a total mass, in this case of 100 solar masses in total in 0.1 parsecs, and some small rotation at the beginning of the simulation. And this time we have a constant magnetic field, in this case of 68 microgauss for this particular example that I will show you in the next slides. And the physical ingredients of the simulation are magnetohydrodynamics to keep track of the gas and the plasma, self-gravity, thermal re-emission by dust and gas, and ohmic resistivity as a non-ideal MHD effect. And the grid that we are using in this case is not 3D, it's 2.5D. That means axisymmetric. There's only one cell in the azimuthal direction, but every field that we compute has the 3 components. And as the sync cell, so our internal boundary, while in the previous case, it was 30 AU. In this case, we are able to reach 3 AU. And there is also equatorial symmetry. There is something important here. The maximum resolution is also sub-AU, is 0.06 AU, very close to the protostar. And this will become important in a moment. So if I run the simulation, this is what we will get. You see in the horizontal, in the middle of that video, the accretion disk, and in the vertical side you see the jet. But I would like to illustrate this with some observations. And here there is a particular region of massive star formation that is of our interest, IRAS 21078 plus 5211. And we will be zooming in and in towards the jet in this observations, and then comparing them against the simulations. And I will also point out that every slide here has a bar where you can keep track of the length to scale. So then we can zoom in here, and thanks to the core program that was done with Noema, we can observe what is the structure inside of the dense parts of this molecular cloud. And here you see I have removed the color information, but this red means that there is a higher emission, so higher density. And so there is some higher density points in this cloud core, even though there is some maybe smaller fragmentation that is visible in there. And if we change not the scale, but the wavelength of observation, then you see the molecular outflow is revealed. And the scale bar there is 5000 AU. I start my simulations with a molecular cloud or a cloud core of size 0.1 parsecs in radius. So that means that this is comparable to the start of my simulations. But here in the observations, one sees the different parts of the observation, the disk and the protostar, one of those yellow contours that is towards the center, the bipolar outflow, and a bow shock that maybe is related to when this jet or outflow was originally launched. But as I was saying, this is more or less the size of my simulation, so I can superimpose here my results from the simulation. So this is the extent of my computational domain. And by putting the arrows here, one sees that most of this is really showing the collapse of material. And there is a relatively slow outflow here, which in the simulations is driven by magnetic fields. This is what we call the magnetic tower flow. And essentially the mechanism goes like this. The magnetic field lines are being dragged by the collapse, the gravitational collapse towards the center of the cloud. And at the same time, they are being twisted because the material, because of the conservation of angular momentum, the material is also rotating faster. And so the magnetic field lines, because they are very twisted, they form a gradient in magnetic pressure. And this gradient in magnetic pressure can be even larger than gravity in the radial direction. And this is what is driving this molecular outflow. But the typical velocities of this are of the order of 10 kilometers per second. So it's a relatively slow molecular outflow. We can zoom into the accretion disk and the jet launching region. And those are, again, some observations with molecular transitions. I have also removed the color information just to tell you here that red and blue here mean Doppler. So we see there is a rotating structure. And there is also a jet. And the forming massive star in this case is 5.6 plus minus 2 solar masses. This is a forming massive star, so it's not yet a massive star. But what I can do is then to look into my catalog of simulations. I produced around 31 of those, and look for the simulation that looks the closest to this, and the time in that simulation where we see a disk of more or less the same size and a protostar at the same time with mass more or less the same mass. And this is the result. You see that this is why the simulation, there is no coincidence that they look alike, because I have dug into the simulation catalog. And here the jet, the high speed parts of the outflows of the jet is quite visible. And this jet is launched by the magnetocentrifugal mechanism. I will explain this in a moment. Then one can see the accretion disk and the forming massive star, more or less the same features as in the observations. And the accretion rate here is 6 times 10 to the minus 4 solar masses per year in the simulations, at least, and is more or less consistent with what we expect from the observations. But then something that was not expected, some little anecdotes. I started to work on this topic of jets during my PhD with Rolf. And Rolf warned me that this is so deeply embedded in the cloud, so opaque, that it would probably never be observed. But I said I really like jets and I really like plasma physics, so I would really like to work on the jet topic. But to our surprise, a few years later, Luca Moscardelli had contacted us with some amazing observations that you've seen here of water masers that, thanks to the VLBI technique, the very long baseline interferometry, so radio telescopes working in sync, information from the center of the cloud has been obtained, and it shows individual streamlines emerging from the disk. So this was absolutely amazing at the time. And the resolution, I will point out, is 0.05 AU, and the simulations only get this resolution very, very close to the forming protostar, but not everywhere. So now actually it has come the situation in which the observations are now ahead of the simulations, instead of how it was for several years, which was exactly the opposite. And with this, then what we did was to compare against the simulations. Here you see in the background a vertical cut of density. This is then showing the accretion disk and the jet. And the blue lines are streamlines that both trace the flow, and in this frame of reference in particular, where we believe the water masers are being produced and leaving this trail, also is tracing the magnetic field lines. So here we also get the magnetic field line information, and they fit quite well. And then the conclusion of this paper was, in particular, that those high velocity jets, at least in very early stages of massive star formation, so before there is any kind of stellar feedback, are magnetic in origin, and particularly they are launched with the magnetocentrifugal mechanism, which I will explain next. And then after that, we did even a more thorough comparison in this other paper, in which we were able to fit even section by section of the streamlines to the simulations. And so the magnetocentrifugal mechanism works like this, is more or less actually very, very similar to what happens in an accretion disk or a jet close to a black hole. But here we have material that is collapsing, so it's very different in that regard, instead of the almost vacuum that you see in other situations. And you see here in this diagram, well, on the left side is almost not visible density, and on the right hand side you see some contours, and the contours separate some two quantities of dynamical interest. So this shaded blue part is where centrifugal force wins in the cylindrical radial direction, and where gravity wins is the other side, which is not shadowed in this contour. And the yellow shadowed contour shows where the flow is subalfenic, and the not shadowed part is where this flow is superalfenic. So if you're not familiar with those terms, essentially means that the magnetic field is being dragged by the velocity field in this outer part, and is the opposite. The magnetic field is guiding the flow inside of this Alfvén surface, so this yellow part. And the idea is then that the material comes, thanks to gravity, goes through the accretion disk, and then when it reaches this point, the centrifugal force wins, so the material should move radially outwards in the sense of cylindrical radius. But because the magnetic field lines are guiding the flow here, the material is forced to follow the magnetic field lines. So the magnetic field lines are more radial, so the flow escapes more radially. And this is the launching mechanism of this jet. And because the kinematic signatures and everything fits quite well, then we know that this protostellar outflows are launched magnetocentrifugally. Very quickly, I will mention the magnetic field strength and direction has been now measured and also compared against the simulations, and they also fit quite well. So I will show you very quickly this idea of feeding a baby massive star. This is very, very recent work. We looked into the Cepheus. In the Cepheus constellation, there is this object HW2, which is a massive star forming region. And again, we compared against the simulations, the same kind of set of simulations, so the same simulation catalog. Before, those were the observations that were made for this object. The inner jet was observed before, but never the accretion disk. So now, with some very nice observations with the VLA, we were able to observe, thanks to some emission lines, the velocity along the line of sight, which is those colors that you are seeing in there, of the material that is moving in an accretion disk way, but the subkeplerian part that is surrounding the keplerian part of the accretion disk. So if I put again the simulations on top of this, then you can more or less make sense of the flow in here. So this is, as I say, the colors show the velocity along the field lines and the flow lines that you see here in the simulation on top of the observations. The measured accretion rate for this system is 2 × 10⁻³ solar masses per year. So this is very exciting because this is a very, very strongly accreting object and has a very strong jet. So this is also something important to match against the observations. In the simulations also we see a very strong jet. And this object has already a stellar mass of 16 solar masses. Although no photoionization yet, but this is most likely about to start arriving into the main sequence. Here you see again the simulations, and I will leave in a moment just some of the details of the simulations that you see in there. Again, a density profile, initial magnetic field, the same as in the other case, and slow rotation initially. And this is, well, the paper and the full research team that I will also mention here. And then I would like to mention some ongoing work. I have to rush a little bit, not to be overtime. But yes, there are several collaborations and things ongoing at the moment. Very, very exciting projects. So one thing that I am able to do from with the simulations is to have an idea on what is the angular momentum transport that the disk, well, is Keplerian, this is quite easy, gives to the forming protostar, but also very crucially, what is the angular momentum that is removed or transported outwards by the jet. And this is something, as I say, it's ongoing work, is going to be ready for submission soon-ish. But I would like to show you, well, here at the left-hand side, you see one of the streamlines and the Alfvén surface. And inside of this Alfvén surface, then following the jet mechanism, one can make a model, a semi-analytical model and tune it with the simulations, which is the right panel that you see in there, for computing what is this angular momentum that is transported outwards. And then the exciting thing that you can do is then to reduce even one scale further down, as you see in the indicator here, and feed this information of angular momentum transport, both inwards and outwards, to stellar evolution code. And this is the job that I did in Geneva, and that I'm continuing to do this at the moment. And then one can compute protostellar evolution models with rotation, in which we take into account what is the jet doing and try to tackle the angular momentum problem for at least the protostellar evolution. And this is very, very exciting. I will show you, even though this is not published yet, I will show you one of those models. And you see as a very early result, we get in the top panel that the angular velocity of the surface is actually capped by the jet compared to the critical velocity. So actually our protostellar model is not going beyond the critical limit, which will happen very, very quickly if you remove the jet. And so this is very, very exciting work that I'm doing with my colleagues in Geneva, particularly with Sylvia Ekström, but also Georges Menet, Patrick Eggenberger, and many other collaborators from my time in Geneva. Another collaboration that is ongoing and some very, very early results that you see here is adding further non-ideal MHD effects for this protostellar jets, because we are very uniquely positioned to resolve this, all of these mechanisms of the jet. And so then we can study with detail what the non-ideal MHD effects are doing. And this is a collaboration with CEA by Saclay, particularly with Hugo Lebreuil and Valentin Valutigua, that developed the code Shark. And now two of my master students are going to keep working on this by implementing and adding this non-ideal MHD effects. This simulation that you're seeing on the left includes ambipolar diffusion. And the work that I continue to do with Rolf's group in Duisburg, and with my former master student, was a co-supervision of a master's thesis, Joshua, who's now in Germany with Rolf's inside of Rolf's group, which is to study feedback from massive star formation. So this can be done with all of these other modules that Rolf has developed, and add magnetic field. So then the idea is to study the interaction between the jets and the other feedback effects, like photoionization and radiation pressure, radiation forces. Well, I would like to close this presentation by inviting you essentially, well, to at least put Costa Rica in your minds, and please come visit us. We can coordinate a visit anytime soon. Of course, this I took this picture a little bit over a month ago, is not so close to San Jose where I am, but this is part of the main campus. It's just a random corner in here. So if you like seeing beautiful landscapes full of many kinds of forest, and to some very nice and exciting astrophysics projects, please talk to me. And with this, I would like to thank you again for this very, very nice opportunity to talk to you and to showcase our work, and be ready for any questions that you may have. Thank you very much.
Okay, thank you very much, André, for this very interesting and nice presentation. So now it's time for questions. We are not many today, so I really encourage people to think about or to take the opportunity to ask this expert on massive star formation. Even, yeah, Andreas.
Very good. Andreas deserves a couple of questions.
Yeah, thanks a lot, André, for a very, very nice and interesting overview. One thing I was wondering in the beginning, when you talked about the disk fragmentation, right? You gave some of the mass numbers and you said those are not final numbers. But from these models, can you learn anything about the mass ratio that would be predicted in binary systems? Because that's often something that's just assumed when people try to model it. But is this something we could get from simulations and then try to compare to observations?
Yes. So in my view, even though those masses are not final for sure, there is going to be in this scenario a massive central star, which would be higher mass than the companions. So this depends a lot on the initial conditions and what happens in the very early stages of the fragmentation of the disk. But you either have one central star that is the center of the simulation, or because we have a single, we cannot rule out having very equal mass binaries, but they have to be very, very, very close together. This is then the point, right? At least in this kind of simulations with these initial conditions, we wouldn't expect a companion with equal mass that is farther away from the central massive protocell, from the what we would call the primary. So you can't draw a final conclusion here, but I will say with our 5 simulations, with the statistics that we assume, how we assume everything is formed, we can say that the mass ratios, well, even though we don't know the final masses, but that there should be a centrally dominated system compared to what you will get from cloud fragmentation, which would be larger separations of a few thousand AU, except if you have some sort of captures, and more equal mass ratios. So this is the situation, because I mean the key argument here is that during this first stage that I'm not showing in this video, which is the formation of the disk. So here the disk is already formed and starts to fragment. Well, the star has a lot of time to feed just before the disk starts to fragment. So already there is some advantage in time just because of this argument. You can imagine always that the fragments that are produced by this fragmentation in particular are going to be always lower mass than the center part. And so this is where the initial conditions play, because they give you a larger or smaller disk, which is more or less massive. It will fragment later or earlier, and this will give you then different kind of distribution of masses at different points in time. So yeah, this part of initial conditions is not fully explored. So I have some ideas on how this works. It has been partially explored in a few papers before, but not really much on statistics and what each initial condition can produce. But actually, that is a very good idea for future projects to present some sort of statistic. It's quite hard, I have to say, but at least I think it might give some light into people who look into multiplicity more. Thank you.
Thanks a lot.
Any other question by the audience? If not, I'm going to ask myself one question. Maybe it's a bit difficult, but yeah, I would like to know your opinion. So on one side, we have what you have shown us about the star formation process that is quite complex, with the accretion, disk, the jets, and then even something that I was not aware of thinking about it, that this fragmentation, that yeah, even I saw in your simulation that sometimes part of these fragments are interacting with the core, and I assume that this is affecting the mass that is accreted by the central star.
Correct.
On the other
Yes.
side, when we go to stellar evolution, we have a very simplified version, and this is why I liked your last slides when you are trying to connect, where, if I'm correct, what you assume is a given mass and accretion rate, and then the star is evolving to the thumbs. And then in the massive star domain, at some point, we know that depending on the accretion rate, then the burning of hydrogen can start or not at some point. So this is modifying if the star is reaching higher masses in the SAMs or not. So the question is, how you reconcile the accretion rate that you are considering in the models of the protostellar evolution with all this? So we don't have a accretion rate, because we also have mass that is move out from this core, no?
Yes.
This question for you?
Yes, yeah, that makes sense. So the the point, as you see, you are absolutely right. Accretion is not really a smooth process, and at the moment, I know that it's not only me, but I at least experimented with Devesh Nandal in Geneva to feed some accretion history into the protostellar model in the Geneva Code. I know that also some people have tried something similar, so we know more or less, or at least there are the first steps more or less to try to find out what happens when you have episodic accretion and kind of huge chunks of matter that can come into the protostar. The problem is that no one is taking care of how this material might be ejected. This is the other part of the question. And this, I have to say, it will have to be something for the future. I am heading into that direction, but definitely is going to be very tricky because you have to connect essentially the simulations that I am showing here, even a 3D version of this, ideally, with stellar evolution code, and then communicate mutually what happens when material enters and what happens when material might be ejected. The thing is that for the rotating case, at least to my knowledge, this is what I'm about to start writing very soonish in a paper. We don't even understand fully the problem of smooth accretion and ejection of angular momentum. And this is why people have not usually even gone into rotating pre-stellar evolution, main sequence models, because there is no easy way to explain this evacuation of angular momentum needed. And there are even several models to consider in this case. But at least for the massive case, I'm for sure going to push this one because there are a few arguments in here to be made. But my point here is that, yes, that is the ideal situation, that we should take not only into account episodic accretion, which a few groups have tried, but also what happens to rotation, in which then you will also have some ejection of mass, because this is one of the parameters you have to assume or measure somehow what is the ejection to accretion rate. So even though you may have an accretion history to feed into a stellar evolution code, you also should know somehow how much of that mass is actually going to stay in. And then follow the angular momentum evolution even inside of the star and see how the redistribution happens, and then do some statistics. So that actually there is a lot of this. Is actually I'm stopping here in a way, because this is going to be the main focus of my research for the next 4 years, more or less.
But you think that this is a second order effect or not? We are talking about something that is going to really change things.
Well, from the point of view of stellar evolution, I cannot say at the moment. From the point of view of the full system in general, so I mean, what I mean with stellar evolution is how much of this is carried onto later stages of the evolution of the star. This is the question that I don't know how to answer. But in terms of the star formation process, for sure, because what you see in at the moment, what we're doing is interpolating some stellar evolution tracks, and yes, the radius is a derived quantity, so the radius is going to change quite widely at those stages where there is a chunk of material going in. And then when one needs to see how stable this is and how to really explain those very strong changes in radius, how much of material mixing is going to happen at those very early stages, even whether a 1D model like a stellar evolution code is still correct for this kind of scenario. This has also been, so those are all questions. So it might happen that we have to explore this with way more detail. I actually don't know for sure at the moment, but yes, I believe that there should be a a huge effect. Question is whether this is carried to the later stages. That I don't know.
So it's great that you have a stable future to continue in this.
Yes, yes.
So we'll see
Definitely. Very
what it
exciting.
shows in the next year.
Exactly.
Any other question by the audience? If not, then let me thank you again for accepting the invitation and giving us this very nice overview. And in any case, if people is watching this nice talk in YouTube and want to ask questions to André, I'm sure he will be happy to answer you back by mail. And thank you
Exactly.
everybody for joining us. See you in 1 month.
Thank you. Bye-bye.